Okay, so I'm going to start now. So the title of my work is ScoreDrivenModels.jl, Generalized Autoregressive Score Models in Julia. And I'm going to start my presentation talking a little bit about the motivation that I had to do this work. I'm going to talk about score-driven models, estimation, diagnostics, and some nuances about the models. Then I'm going to talk about the computational package that I developed. And I'm going to discuss a little bit one application of my package. So beginning with the motivation, in many decisions under uncertainty, it is common to consider different scenarios of demand generation, production, climate, whatever it is. You usually need some model of a time series to estimate, to generate future scenarios. And usually these scenarios are used to answer some questions such as, should I build a transmission line here? How many newspapers should I buy to maximize my profits tomorrow? Should I carry an umbrella to work tomorrow? And things like this. And great question is, how do I generate these scenarios? Which models do I use? And when I generate all the scenarios and make probabilistic forecasts, how do I compare two different models, two different probabilistic forecasts? So scenario generation and probabilistic forecasts require very flexible time series models. So a natural candidate for such tasks are score-driven models, because they have some desirable characteristics, such as considering discrete and continuous distributions and having time-varying parameters. And this allows for a lot of flexibility in terms of modeling, in terms of what are the time series that you can model and what are the specifications and ideas that you can explore within this framework. So more about score-driven models. The context of score-driven models, they're also known as generalized autoregressive score and dynamic conditioning score. And this class of models was simultaneously proposed by Creal, Koopman, and Lucas in 2013 and Harvey in 2013. Fun fact is that Koopman was a student from Harvey. So they're actually more or less the same group, but they had different approaches to it. Although all the nuances of the models, the estimations and everything are the same in those two works, they model different dynamics and have close but not quite the same approach to it. So a little bit about it. In score-driven models, you generally assume that observations comes from a certain distribution and that the parameters of the distribution follow a certain dynamic. And this dynamic is usually driven by the score. So in my notation, I have here an F, that is a big F, that is the set of all the past observations and past parameters of the distribution. We assume that the observation comes from a probabilistic distribution function that considers these parameters of the certain distribution, and that we have a certain function G that updates the parameter of the distributions at each time step, and this function usually depends on the score. Not only the score in time t, but it can also depend on score of more past observations, more past timestamps. And the score is the derivative of the log of the probability distribution function with respect to the parameter of the distribution. These dynamics, this is just a picture for illustration, these dynamics allow that the observations comes from a same family of distributions, but with different parameters at each point in time. So you can change the location, change the scale, change the shape, and things like that. So the distribution evolves over time. So more specifically, I'm more focused in my software in gas PQ. That was the model proposed by Creal, Koopman, and Lucas. And this is the updating dynamics for the gas PQ model. You have your parameter, f, at time t plus 1, and it is equal to a sum of a constant, some scaled score, and past parameters. And this scaled score, it is given by this Fisher information to the power of minus d times the score that I showed you before. And when studying these models, they realized that by changing the scale d, the scaling parameter d of the distribution, they got some well-studied models in the literature. In particular, if you have a gas PQ Gaussian model with d equals 1, and if you assume that the location parameter, the mean of the Gaussian distribution, is time varying, you actually reach to an ARMA PQ model that was described by Box and Jenkins in the 70s. If you have a gas 1-1 with a Gaussian distribution, normal distribution, and if you make the scale parameter, the variance, as time varying, you reach to a Garch 1-1 that was proposed by Boleslav in '86. And if you have a guess one with exponential distribution and d equals 0, and well, it only has one parameter as time varying, you get to an ACD. Is a duration model proposed by Engel in 1998. So this kind of model, they allows for high flexibility in terms of modeling. And this is very useful in the context of decision under uncertainty. One example that I give that I will further discuss in my application is to make probabilistic forecasts of the effluent natural energy, which is a strictly positive variable that is very used in the context of the energy sector in Brazil. They model the energy in the reservoirs of every hydropower generation in certain regions. So if we have the approach of doing this with Gaussian models, more classic models such as a SARIMA or a basic structure model, many times what happens is that you have observations that are not strictly positive, or scenarios or prediction intervals that are not strictly positive. And if you deal this with, if you assume strict distributions in your score-driven models that have a positive support, you mitigate these kinds of problems. Of course, that you can do other things to make the strictly positive forecast, but this is one good approach. So a little about some comments about the parametrization is that, well, in score-driven models, the updating mechanism, many times it can't lead to invalid updates, such as making the scale parameter of a Gaussian distribution negative, which is not a valid parameter, is not a valid is not a valid space for these parameters. And for this reason, usually one has a map, a function h, that ensures that the distribution parameters stay always in a viable space. So instead of making the updating mechanism in the original parameters, you make the updates in the mapped parameter. In particular, for a Gaussian distribution, it's very common that you map with a log, the natural logarithm function. And now the updating mechanism becomes an updating in the natural logarithm functions. And it's important to recall that when you make this transformation, you are actually changing a little bit the dynamics of the model. So if you make this change in the Gaussian 1-1, once you make these updating steps, you no longer have a Gaussian 1-1, but you have a closed model. And whenever you adopt the certain parameterization, you need to adopt everything else. So you need also to adopt the scaled score. And in the paper of Creole, Koopman, and Lucas, they discussed it a little bit. And this is the counts. This is the math that you must do in order to adapt your updates whenever you have a different mapping function than the identity. So just some examples, just to be more clear. Suppose we have a Gaussian 1-1 distribution with the location, the mean as a time varying parameter, and the scaling d equals 1. Well, the first approach in the workflow is to pick the probabilistic distribution function of the Gaussian distribution. You compute the logarithm of this probabilistic transfer function, and you evaluate the score and the Fisher information. Then you write this dynamics. So these are the dynamics of this particular model that I wrote in this slide. Another example that we could make is a distribution, a Poisson distribution with the lambda as a time varying and d equals 0. So you make it the exact same process, but this time notice that the lambda is strictly positive. So whenever you are calculating the score, you put the original score, but you add one term here that is correcting for the change in the variable for modeling the log of the parameter instead of the parameter itself, and assuring this way that the parameter remains always positive no matter what updating, no matter what hyperparameters you are estimating. So, okay, this is a little bit about the dynamics, and now about the estimation processes for score-driven models. One good approach is to estimate the hyperparameters via maximum likelihood. So in maximum likelihood, you're just maximizing the log likelihood of the distributions at each time step. This is usually done with global optimization methods such as LBFGS or Nelder-Mead or interior points Newton. And many of these methods require gradients and hashes. Usually they are numerically estimated using finite difference method and handled directly by an optimization toolbox that you wish to use. So if you use Julia, you're probably using Optin. If you use Python, you're maybe using SciPy. If you're using R, maybe Optin. And for every language, usually there exists an optimization toolbox. And it's also a good practice to provide different initial values for the optimization and do this optimization multiple times and then see if all these initial values, they converge. This is a way of trying to mitigate the possibility of attaining a local optimum instead of a global optimum, which is the desirable answer that you wish from this optimization problem. Forecasting. In order to do forecasting, k steps ahead forecasting, usually for k greater than 2, in score-driven models, it is a process done by simulation. So the version implemented in our work is the simplest one that only accounts for the innovations uncertainty. We ignore the hyperparameters uncertainty in our implementation. So given your estimated parameter steps ahead and the last filter state f of t, big T minus plus 1, you simply draw s values from the distribution function of parameters ft plus 1, and then you can continue to update you can continue to calculate the score and continue the updating mechanism until you have a lot of observation scenarios and a lot of parameter scenarios as well. So you use exactly these observations to continue the update mechanism and obtain new featured values. And then you repeat these steps until you reach the k steps that you wished for in the first place. Diagnostics in our framework, the diagnostics of score-driven models are done usually using quantile residuals. So under correct specification of this model, the probability integral transform, the pitch, it follows a uniform distribution, and we can obtain quantile residuals by applying the cumulative density function of Gaussian distributions in the probability integral transform. So once you do that and you obtain the quantile residuals, you can proceed to apply common statistical methods such as Jacques-Beer and Bloom-Box to verify classical assumptions as the residuals should be normal under this correct specification. You should have no autocorrelation between in the legs and things, other classical methods, classical tests that you do in time series. So this is a little bit about the framework, how we estimate, how we model, and how we diagnose the model. So now a little bit about the ScoreDrivenModels.jl package. So we decided to make an open source framework. So other people in the Julia environment, and in any environment at all, can experimentate and integrate score-driven models in the decision under uncertainty software. So usually, as I stated, you are not only interested in making the time series prediction forecasting, the probabilistic forecast. You are usually interested in making a decision with them. So this is a good opportunity for you to integrate these kinds of models in your whole framework, where you will come out with an optimal decision for your problem. So we chose Julia. Julia is an open source language that started in MIT in 2012. And the main goal of the creators was to solve the two-language problem. The goal was to create a programming language that was as fast as C and as easy to write as Python. And it is a language very focused on numerical computing. Here are some benchmarks of the time to evaluate some different algorithms in different languages. And you can see that Julia has a time of computation that is very comparable to C and other modern languages such as Go and Rust, and other classical numerical computing languages such as Fortran. And they are usually faster than algorithms written in Python, even sometimes even though using NumPy and R. And so the goal was to be construct a framework that was entirely in Julia. It was easily hackable. So anyone that is studying score-driven models could enter that and maybe fork the repository and make its own modifications and profit from all the scores and all the things that are already implemented inside there. And this was a goal because I saw other score-driven models open source frameworks such as the Argos package and PyFlux, and they usually use lower level languages. So R, the framework in R, they usually use C++ under the hood, and the PyFlux method, the PyFlux project, they use Cython, that is a combination of C and Python, to obtain higher performance in their framework, higher performance in estimation and forecasting. So the software provides some desirable features for practitioners, such as modeling and estimating gas PQ models for continuous and discrete distributions, using different parametrizations for distribution, initial parameters heuristics, diagnostics via quantile residuals, full k-steps ahead distribution forecasts, and comparing the forecasting performance of different gas models. And it also contains different visualization routines. So these are just functions that you can just type like plot model and it will give you a lot of things, and you won't have to build complicated plot recipes for your project. So a little bit about the software. This is the way that you model in our software gas PQ distribution. You just say that you have a variable gas in the global model. You give the lag structure. This can be integer numbers, or it can be a vector of integer numbers. Whenever you pass a vector of integer numbers, usually you are assuming that all the other lags between them that are missing from the biggest one are just considered 0. And this is usually good to speed up things, speed up the optimization and the code as well. And then you give the distribution, and then you tell what scaling do you wish for your gas PQ model. You can also indicate what are the time varying parameters that you wish. So in a Gaussian distribution, in a gamma distribution, for example, if you wish that the time varying parameter is the first one, you're saying that I think one of the scale parameter will be considered time varying. So in the software, I implemented several distributions. This is the list of distributions and what are the possible scalings for each one of them. These ones that don't have inverse and inverse square root scaling, it was because I haven't implemented yet the Fisher information for them. So we have a beta function, which is a very interesting one because it is bounded. You have a lower and an upper bound for the support distribution. You have an exponential distribution, gamma, log normal, normal, Poisson, T, and Weibull. These are the main ones. So once you have instantiated your model, told the software what model you wish to do, you can just fit and estimate all the parameters. And here you can use all the different optimization methods that are available in the Julia optimization package, global optimization package optim.jl. And you can also inform how many initial values do you want to provide to them. If you make this syntax, you are actually you're asking the software to put 5 randomized initial values, but you can also pass all the initial values for the optimization. So one thing to consider when estimating gas models is that as the model contains lags, you must know beforehand the first parameters of the distribution. And the best way to choose these values is it is still a research topic. It doesn't have a work that say this is the best one that everyone should use. It is optional, and they have a lot of options. So 3 possibilities of what you can do. You can consider them as hyperparameters, and estimate them with the other parameters via maximum likelihood. You can provide the unconditional mean of the parameters. That is a simple calculus that you can do with the updating equation, or you can calculate them heuristically. And there are various possible methods on how to calculate them heuristically. In particular, since we're interested in many seasonal time series, we provide one heuristic in particular that we thought was helpful to robustify the estimation process of our software. So, and currently it's not possible to consider them as hyperparameters. The first option that I did is considered a future work. So, as I stated, since we're interested in many seasonal time series, and methods, the unconditional mean was a little bit bad approximation for many distributions. So we designed the heuristic that usually helps to robustify the process. And the idea is to separate the time series in seasonal groups and estimate the parameters of the distribution via maximum likelihood. So in the alpha natural energy time series, in this example, to estimate the first two parameters, or for example, a log normal distribution, you simply take all the observations in January, and then you have a time series, you have a bunch of observations, and then you can fit a constant log normal distribution using maximum likelihood estimation, and use them as the first parameters for your estimation process. And then you can repeat this for all the following months until you reach all the legs that you need. If you make a model with 12 legs, you need 12 initial parameters. And once you estimate it and everything is fine, you can ask for diagnostics. And diagnostics mean you can query the log likelihood that it was estimated, the information criteria, the Kite information criteria and the Bayesian information criteria. You can see the point estimates of each hyperparameter, and you can also see their confidence interval. And then you can also plot the quantile residuals, the histogram of quantile residuals, the autocorrelation function of the quantile residuals, and a quantile plot, a QQ plot of the quantile residuals to understand if they are Gaussian as expected. So, okay. And once you have all these confidence intervals, you can also query the quantile residuals and use other Julia packages such as hypothesis-test.jl, which is a big Julia package to apply many statistical tests such as Jack-Beta and Young-Box. And if you wish, you could implement a lot of others such as augmented Foley and any statistical test that it is interested in particular. Usually Jack-Beta and Young-Box are okay for diagnosing ScoreDriven models. And okay, once you have the diagnostics and you think you're ready to make a forecasting, you can just go on and make the forecast with this simple function forecast, and then you can query all the parameters that you forecasted, all the observation scenarios, the observation forecasts, the scenarios of parameters, and so on. And you can also filter. You can also obtain the mean of the distribution that you fitted. So this is one way to obtain the filtered mean of the model. And you can also obtain the parameters that the score-driven recursion, the updating mechanism, gave with the optimal hyperparameters. Okay, so one thing that I discussed earlier is that another problem is how do you compare two different models? So one way to compare two different models is to backtest, to make a lot of different backtests and evaluate the forecasting performance of the models using rolling time windows. So usually what you do is that for a lot of different time steps, you separe your data set in training data and test data, and you make the forecast and try to evaluate the forecasting performance of the predictions that you made. And when dealing with deterministic forecastings, it is common to use metrics such as mean absolute error or the MI or the mean absolute percentage error or the MAPI to benchmark lead time the forecasts. But when you have probabilistic forecasts, this is a little bit harder. So one of the principles that one need to understand is that the perfect probabilistic forecast is that you have all the mass distribution in the correct point. And based on this idea, they came up with different scores, different forms of scoring. How do you compare gave a forecasting performance of different distributions, considering that the correct distribution would be the full probabilistic mass in the correct point. And two common ones are the CRPS, continuously ranked probability score, and the pinball loss function. So we decided to integrate directly in our software the CRPS, which was proposed by Madsen and Winkler in '76. and it is this integral here that is basically a metric that calculates a certain kind of distance between the true probabilistic density function, the perfect one, and the probability, the density function that you provided. And this can be made in terms of scenarios. You can compute this discretely. So then when you have this metric, you can evaluate the CRPS or some any other metric for all the steps ahead across a rolling window horizon. So with all the CRPS evaluations, you can take the average per lead time. So you make a forecast for 60 steps ahead, suppose, and then you take the prediction, the CRPS of each of one of these steps ahead that you made, and then you keep integrating in the rolling window horizon until you have, like, suppose 10 forecasts for one step ahead, 10 forecasts for 2 steps ahead, 10 forecasts for 3 steps ahead, and then you take you can simply take the average to compute a mean CRPS of the model that you proposed. And this way you can compare the forecasting performance of different models in terms. One very good comment on the CRPS that gained popularity over the years because it is a generalization of the mean absolute error. So if you consider that your distribution is the full mass distribution, is a deterministic forecast, the full probability function, in another point, when you do the same, the integration, the CRPS, you're actually getting exactly the same metric as the mean absolute error. So this is one of the interesting features of the CRPS. And in our program, we show that we can easily compare the forecasting performance of 2 competing models with very simple code. So here I made a gas model for a series of the inflation rates of the US and compared gas 1-1 with the student T distribution and scaling 1 with the only time varying parameter as the location parameter, and a gas 1-2 with the same specifications. And then I said, well, let's try to understand the forecasting performance of these models in 50 steps ahead. And I want to start on my rolling window scheme in the observation number 150. And then I simply, after defining the models and the number of steps ahead in the first index, I can just proceed to make 2 back tests and then plot with a very simple plot recipe that we made that compares the forecasting performance of both of the models. So in this particular example, we have this CRPS over time graph and indicating that the mean CRPS for the gas 1-1 student T model, it is better than the mean CRPS for the gas 1-2 student T model, indicating that if you wish to make forecast, in all of the lead times, it is better to make a forecasting by these criterions. It is best to bet on the gas 1-1 model to make the forecasts. So the software is also very extensible. One can add new distributions or even new parametrizations by implementing or overwriting just a few methods. So in every model, in every distribution, you have to specify the score, the efficient information, the log likelihood. You can specify the parameterization choices of for this particular distribution, indicating functions of link and non-link and Jacobian link. These are the maps, the inverse maps, and the derivative of the map. And you have some helper functions just to help the software at all. Just how do we instantiate another a similar distribution with different parameters, querying what are the parameters of your particular distribution at some point in time, and querying the number of parameters of that distribution. So, okay, one application that we did in the software was to try to forecast, to make scenarios for 60 steps ahead, meaning 60 months or 5 years of the affluent natural energy in Brazil, in the Brazilian subsystem. In particular, this one is the northeastern Brazilian subsystem. And as a first choice, we use a log normal model with a tailored lag structure. So this is the log normal distribution. And we said that we have a gas PQ model, and we're only considering the 4 first legs for the score part. This is a guess 4 and a tiered leg structure, and considering the 1, 2, 3, 10, 11, and 12 legs for the autoregressive parts for our cube. And this is the dynamics of our location parameters, and our scale parameters, they are just constant over time. This was our assumption in this model. And as we see, it's very simple. We defined this model that was written in the other slide with this simple code. We can use the dynamic initial parameters heuristic to calculate initial parameters and estimate these initial parameters using the function ScoreDrivenModels.fit. And once we do this, we can also obtain all the diagnostics of the model and understand if we can improve the leg structure or we can change our distribution. We can do something that takes some action in our modeling task. And then once the model is estimated and you're happy with the diagnosis, you can simply simulate and make probabilistic forecasts and scenario generations with the same software. So, okay, the conclusion is that, well, score-driven models is a package that provides a fairly general framework for score-driven models and represents a user-friendly, off-the-shelf tool for practitioners. So the software is a great place to start when designing experiments in score-driven models, and since it is open source, it can be used by the industry or by other researchers as a tool in their analytics squads and products to productize and implement this kind of methodology inside your decision on uncertainty framework. And well, although I am happy with some of the features of the package, we have still many features to evolve. The software continues under developing, and there are some features that are still missing that I feel a little bit of pain missing, such as the inclusion of explanatory variables inside this framework, the unobserved components dynamics. So the unobserved components is more like an approach of some papers of Harvey. I think that Time Series Lab also uses what I call an unobserved components dynamics. The ability to estimate initial parameters of the distributions via maximum likelihood. Implement heuristics to choose good initial points, not only just randomize, just pick like 10 random initial values and try to see where the optimization converges, but try to implement heuristics to choose good initial values for the optimization. We should add new distributions such as the scale of the Bernoulli, and we should rewrite some of the optimization routines to exploit Julia differentiable programming features. So this would accelerate a little bit the estimation part, making that the gradients and ascents are not calculated using finite differences methods, but by using forward and backward differentiation methods. Automatic differentiation is a topic that is under a lot of research in the world in general. And add different versions of existing distributions where one of the parameters is the location. But because we have, for example, the gamma distribution, the version that is implemented, I think, is scale and shape, the two parameters. And we could also rewrite this distribution to have one of the parameters as the location, which is usually a good feature to have. And the last thing is to add missing value support. In the last semester, I studied a little bit more of the simulation methods to deal with missing values in score-driven models, and I totally think that we can implement them in our software. So